Have you ever pulled out an older laptop from a cupboard and been mildly amazed at how many ports lined its edges? A full-size USB port, an Ethernet port, a memory card slot, a separate headphone jack, sometimes even a DVD drive, compared to the 1 or 2 openings on the side of a current model. The official story is usually about minimalist design and modern wireless convenience. The deeper reason is mostly about something far less glamorous: structural engineering and the physical limits of how thin a chassis can actually be. Every port cut into a laptop's chassis is, mechanically speaking, a hole in an otherwise continuous, load-bearing structural material. The thinner a laptop becomes, the less material surrounds each hole, and the weaker the chassis becomes exactly where ports sit, precisely the edges most likely to be bumped, dropped, or flexed during everyday handling. But here's the surprising truth. As manufacturers pursued increasingly thin laptop designs over the past decade and a half, driven partly by genuine consumer demand for lighter, more portable devices, and partly by competitive pressure to make each new generation visibly slimmer than the last, the structural cost of maintaining a full complement of legacy ports became a real engineering constraint, rather than a minor inconvenience. A chassis riddled with multiple full-size openings along its thin edges is measurably more prone to flexing, cracking, and structural failure under everyday stress than the same chassis with fewer, smaller openings. Think of it like a wall in a building that needs several large windows cut into it. Each window is a structural compromise, requiring additional reinforcement around its edges to maintain the wall's overall strength. A wall riddled with many large windows close together becomes significantly weaker overall than the same wall with fewer, more carefully placed openings, regardless of how useful each individual window might be to the people inside. Removing physical ports also directly improves a laptop's resistance to dust and liquid ingress, since each opening is a potential entry point for contamination, and reducing their number simplifies the internal sealing required to achieve genuine water or dust resistance ratings that manufacturers increasingly market as a selling point. So, if the structural and durability arguments are this genuine, why do manufacturers frame the change publicly around minimalism and modern aesthetics, rather than chassis engineering? The answer, as is often the case in consumer technology marketing, comes down to which explanation resonates more positively with a buyer standing in a shop deciding between 2 visually similar laptops. Describing a thinner laptop as more elegant and modern sells considerably better than describing the same design choice as a structural compromise necessary, because the chassis could not safely support as many openings at the reduced thickness customers were demanding. Both explanations are accurate descriptions of the same underlying engineering reality. Only one of them was ever likely to appear on a product page. The single remaining port on many ultra-thin laptops, almost universally a USB-C connector capable of carrying power, video, and data simultaneously through one small, structurally minimal opening, represents the practical compromise manufacturers settled on. A single hole doing the job that several separate, larger holes used to do, sacrificing the convenience of multiple simultaneous connections for a chassis that remains structurally sound at a thickness that would not have supported the older approach at all. So the next time you find yourself reaching for a dongle to connect a single device that an older laptop would have accepted directly, you will know the missing ports were never purely an aesthetic choice. They were holes the chassis could no longer structurally afford to have, at a thickness the market had been demanding for years before the engineering finally caught up with the consequence.